Good evening, everyone. So, welcome to week 12 of the NPTEL session for the course Electrical Machines 1. For the last 11 weeks, we have started our discussions with transformers concepts, and for the first 6 weeks, we have discussed transformers, several concepts on transformers. And from week 7, we started discussing DC machines. We started DC machines with winding, how the winding for the DC machine will be done, and then we move to some parameters and some winding terminology that will be important to know about the DC winding and DC machine winding, and then we started discussing concepts on DC shunt motor, DC series motor, and we solved some numericals on that as well. So in between these two topics, we have looked at the power flow diagram, like starting from the input to the machine to the shaft output. So what is the power flow and what losses we will be coming across in the DC machine, we saw that as well. So today what we will be doing will be a small session on DC shunt motor, where our power flow concepts will be coming into help. So with that, we will start the discussion for today. And as I said, the concept of the power flow diagram we discussed before. So just to brush up that topic again, let's quickly discuss the power flow diagram for a DC machine, and we will see what losses are there in a DC machine from the input to output, and then we will proceed with the DC shunt motor discussion. So yeah. So let's say here I'm giving my supply. So yeah, I'm just drawing a supply of, I will just, let me draw a DC machine here so that we will see what are all the this is supply to the armature. So here we have armature resistance, and this is back EMF. Let's say this is RA and this is EP, back EMF, and here we are having field winding, and let's say this is RF, and this lens, let's say we are giving here field supply, this is supply to the field winding from here. So these are all the parameters. Now if we see the current flowing through the field winding, let's say IF, and the current flowing through the armature is IF. With that, now we can clearly say the total input to the supply will be total input, that is from the input from the armature side. If you see, the input is VA multiplied by IA, that's the power input power, and from the field supply the input is VF into IF, that is total supply power we are giving, VA IA plus VF IF. So this is the total power input we are giving to our machine. So yeah, but if you see the IF and IA may vary based on the connection. Since it is a separately excited, IF is different and IA is different. For that matter, if it's a series motor, the field winding will be in series with armature, and IF is same as IA, and that is same as load current, that is supply current. Now if it is a shunt motor, yes.
Sir, this circuit diagram is a separately excited DC motor.
It's separately excited. So because the field winding is not in series nor in parallel with an armature.
Okay, sir. Proceed, sir.
Yeah. If it is a shunt DC shunt motor, our field winding will be in parallel with the armature, and the total supply current drawn from the supply will be divided into armature current and field current, that is shunt current. So there supply current will be summation of IA and IF. In series motor, supply current is same as IA, same as field current, but in the separately excited, so we will have separate IF and separate IA, that will not be dependent on each other. Now with this kind of topology, I'm just showing it here. It is the total input to the machine will be input power is VA plus VFIF, and I will just write heading. Please. Power flow diagram. Just quick look back for the power flow diagram because that we will be using it today. Yeah. So the first loss we talked about that day is field copper loss. That means the I square R losses in the field winding. How to calculate I square R loss? The current flowing through the field winding here, that is IF square multiplied by the field resistance, that is RF. Now is equals to IF square multiplied by RF, which is same as VF into IF. This we call it as field copper loss. And yeah, now next we talked about armature copper loss. Some power will be lost in the armature. Now what is the armature current flowing through IA square multiplied by RA? We can't write it as VA into IA because that's not the total voltage. The voltage VA is across EB as well as RA. So yeah, we can't write it as VA IA. And this is armature copper loss, because since we VFIF is neglected here, so VFIF is already taken care of. Now the rest part is VA into IA. So here we are having VA into IA. What we can say, VA into IA is power input to armature. Total power input to armature. Out of this VA IA, we are losing some copper loss in the armature winding, that is I square R loss, that is IA square into RA. Now moving forward, we will have another loss which we discussed is rotational loss. These are the constant losses. Whatever may be the winding, these losses will always be there. Even if there is load or no load, these rotational losses will be there. Do you remember what all losses constitute this rotational? That day we talked about losses of rotational. We even discussed what all losses comes under this rotational losses. Do you remember? If anyone remembers, they can unmute themselves and tell me. Okay. So these rotational losses are constant losses. The losses which comes under these are friction losses, windage losses, and eddy current losses. So these are constant losses. So these are all the losses present in a DC machine, and what power that is left will at the output is P mechanical net. After removing the copper losses, both field and armature, the power which left is mechanical, but it is gross power. Gross is total power including the rotational losses. If we also remove rotational losses from the gross, we will be arriving at the net, which is actual useful power at the shaft end. Now whenever in the problem, if you see a 5 kilowatt motor, a 8 kilowatt motor, a 10 kilowatt motor, that is a rating of the motor, that is a rated power of the motor. Always it talks about the shaft power or output power. So it is very important. You should not get confused with the power ratings given in the problem. Now whenever you come across a numerical a 10 kilowatt DC shunt motor, you should not think that 10 kilowatt as an input to the motor. It's not this value. It is this value what they talk, because that's a useful power. We should not consider all the losses while we talk about ratings of a motor. That is a shaft power, that is the useful output power. Okay, yeah. Now once again, the important point to remember is, once we neglect the field copper loss, the power which is left is called the power input to the armature, that is VA into IA. Once we remove the armature copper loss, the power left is mechanical power, gross mechanical power. and again if we remove the rotational losses, the power left is net mechanical output power. And yeah, with this introduction, with this just quick look back at the power flow diagram, let's discuss DC shunt motor numericals. Just before going to DC shunt motor numerical, let's just quickly draw how a shunt motor will look like, what are the current equations in it, and what are the voltage equations in it. Okay, you all know how a shunt motor will look like. And let me just draw armature first. And this is the armature resistance, this is back EMF, RA, plus minus EB, and these are the brushes. Now it's a DC shunt motor. It means that the field winding is in shunt position to the armature. Here you are giving supply. Now this V is equals to VA is equals to VF. From what we have seen in this diagram, VF is different, VA is different, but here it's in parallel. So all the supply voltages are same. Now if you see, let's say IL is equals to supply current. Let's say my total machine is drawing IL from the supply, and part of the current will go through armature, which is IA, and that remaining part of current will go to field, that is IF. Now IL is equals to algebraic sum of IA plus IF, simple KCL, current division law. And now I can write V as, V is same voltage across armature as well as the voltage across the shunt winding. Now there will be two expressions for V. I can write it as IARA plus EB, right? And I can also write V as IF into RF. Since these equations are applicable only for shunt motor, because the same voltage is appearing across both field winding as well as the armature winding. Okay, yeah. Now what else are important points in this? Yeah, that's it. So with this a little introduction, let's look at two numericals on the DC shunt motor, and we will also discuss how can we calculate the efficiency of a total system. For efficiency, you know how will you calculate efficiency? It's output power by input power. We can know for a given X amount of input power, how much power we are getting at the output. That will give us the efficiency. If it's a 10 kilowatt input I am giving, if I am getting total 10 kilowatt at the output, it's 100% efficiency. But that doesn't usually happen, because you know, we just saw the power flow diagram. We have three different losses along the way. So some power will be lost at each section. So we will be ending up with some power excluding the losses. So we are losing some power at the losses, and we will calculate the output power by input power to get the efficiency. Right? Now let's get into the problem quickly. Please read the problem along with me and analyze what data it is given, and let's infer what data from the problem, and we will see what it was asked in the question. Now at no load, so it was saying that machine is at no load, running at no load, 2.5 kilowatt 150 volts DC shunt motor. Now I already told you it's a 2.5 kilowatt motor, means that power is referring to the shaft power, that is mechanical net power, net mechanical output power. So we already know how much output my motor is getting at the shaft end, 2.5 kilowatt, okay, 150 volts, okay, that's the supply, and it's a DC shunt motor. Okay, now it takes 2.5 amps current at no load. It means that it is taking 2.5 amps at the supply end. From the supply it is taking 2.5 amps. Hello.
Yes, sir.
Hello, can you hear me? Okay. Yeah. So let's draw how it's look like first. It's a DC shunt motor. Again, I'm trying. You also please draw with me, take a pen and paper and draw. So it is given that it is 150 volts and we have armature resistance and we have this one RA. How much is RA? It is 0.4 ohms and EB we don't have, and field resistance is 200 ohms. Okay, estimate and also what else it given? TC shunt motor takes 2.5 amps at no load current and it runs at 900 rpm. That's the no load speed. Okay, now estimate the efficiency at rated load. The data was given at no load and the question asked was to calculate the efficiency at the rated load. Now let's see how we can solve this question. Let's quickly write that all the data given here. Okay, it's a 2.5 kilowatt machine, 150 volt supply, and supply current at no load is given as 2.5 amps, and the speed, capital N is speed in RPM. Okay, at no load is given as 900 RPM, and armature current is 0.4 amps, ohms, sorry, and the field resistance RF is 200 ohms. Okay, now what is the question asked? Efficiency, eta is a symbol for efficiency in percentage at rated load. Efficiency rated condition. Now we know the formula for efficiency. That is output power P output rated divided by P input at the rated condition. Now in this one we already know the numerator, which is equals to 2.5 kilowatt. We just have to calculate the input rated power and then we will take the ratio. That is simple. Now let's see how we can calculate this input rated power. Let's solve for input rated power. Now can anyone tell me the formula for input rated power? Okay, let's go back to the power flow diagram. So here you can see this is the total input power, VA-IA plus VF-IF. Okay, since it's a shunt motor, VA and VF are same. Now if I take both common, that is V here, V IA plus IF. So this is the total current. So IA plus IF is nothing but the supply current the machine is drawing at the rated condition. Okay, now P input rated is equals to V into IL. So this is the supply current, and you should not confuse this IL with this IL. These two are not same because it is a no load condition, but this is a rated condition. Okay, so V multiplied by IL rated is equals to IA rated plus IF rated. Now one thing I want to tell you is this field resistance will be same no matter what the loading condition is. Even if it's loaded or no load, this field resistance will remain same and my supply is remain same. So the amount of current flowing through my field resistance will be same even if it is no load or loaded condition. IF no load and IF any load is always same. It is equals to how much is this current? Voltage 150 by 200. How much it is? 0.75 amp. Now this is a field current. It will be same for any kind of loading condition. Now since since we already know the field current, we just have to calculate IA because we already know V, we know IF. Our calculation is just to find the armature current. Armature current at rated condition. Now let's see how we can calculate the IF. Now I will write an equation from power flow diagram. From the power flow diagram, I need some relation between this armature current and one second. I need some relation to calculate this IA. Now if you see this power flow diagram, the power input to the armature is VIA. It is equals to armature copper loss plus rotational copper loss. Okay, so this power input to the armature, as we see here, is nothing but VAIA is equals to my total mechanical output power available at the shaft end plus the losses we have at that till that point, that is rotational losses and also the armature copper losses. Now with that relation, I am writing this equation here from the power flow diagram. V multiplied by IA. Right, this is the power input to the armature, is nothing but my output shaft power, that is P net mechanical plus rotational losses plus armature copper losses. Right? Why I am writing this equation? To just to get a relation with respect to IA so that I can calculate IA. Now let's see what all we know in this equation, what all we don't know. Now we know V, we have to calculate IA, and we know net mechanical output, which is nothing but 2.5 kilowatt. It's given in the question. We know this. And armature copper loss, of course we don't know it because it's IA square multiplied by RA. That's the point. We have to calculate IA and we know RA. If we calculate rotational losses, because we don't know the rotational losses, if we can calculate the rotational losses, we can have a complete equation in IA, a quadratic equation. Then we will solve for IA and then we will substitute it here and then we will calculate P input rated and then we can get the value of efficiency. So what is that one quantity we require to get the answer? That is rotational losses. Now we know how to calculate this rotational losses. Now we already talked about no load condition. From the data we are having how much my motor is taking at no load. So let's calculate the total losses at the no load condition. At no load condition, I don't have any input. Whatever supply my motor is supplying is only to contribute for the losses. Now for that, let me write a no load losses equation. That will give us the rotational losses. So yeah. Okay. No load condition I am writing. P loss at no load is equals to my copper loss in the field winding under no load condition, my armature copper loss at no load condition plus rotational losses. So this will be constant at load or no load. That's why if we can calculate these three, we can calculate the rotational losses here, and then we can get the we can proceed with the calculation. Now see, at no load condition, in the date from the data, if you see, we were provided with the total 2.5 amps that is taken by the circuit. I will just quickly draw DC shunt motor, and under no load condition, this is 150 volts. Load is not connected across the motor. Now it is given that the motor is drawing 2.5 amps, and what is the field current? We already calculated field current. It is 200 ohms. 150 divided by 200. It is 0.75 amps through the field, and the remaining current, which is 2.5 minus 0.75. How much it is? So 2.5 minus 0.75, 1.75. So 1.75 amps is flowing through my armature. This is under no load condition. Now with this information, we can easily calculate the rotational losses. How? See, what is the total no load loss? We can see at the input side, 150 into 2.5. 150 into 2.5 is equals to, what is the power loss in field? I square R you can do, or V square by R you can do. I will do just 0.75 square multiplied by field resistance 200. What is armature copper loss? I square R again. 1.75 square multiplied by armature resistance is 0.4 plus P rotational. Can you also calculate with me and tell me how much you are getting rotational losses? You can match the answers. Oh, please calculate with me rotational losses. (150 to 2.5), that is 375 minus 0.75 square into 200 minus 1.75 square into 0.4. How much you are getting rotational losses? 261.275 watts. So please tally this value with me. So now what's the next step? Now it's all simple. We have everything. Now we got the rotational losses, and we will get a equation in IA. Now let's say this is equation number 1. Now substitute P rotational losses in equation number 1. Now what is the equation? V into IA. V is 150 into IA is equals to P net mechanical. It's 2.5 kilowatt motor plus P rotational, which is 261.275 plus IA square RA. IA square we don't know, RA is 0.4. 0.4 into IA square. Now this is a quadratic equation in IA. This is a quadratic equation. Now please solve for IA and tell me what's the possible value for IA. Now, okay, you also check with me. I have got two values, that is 355.58 amps and 19.413 amps. Out of these two, which is feasible value? Which value should we take? 300 plus amperes or 19 amperes? It's simple. So this 300 amps is not a valid number to take, because it's too huge amount of current flowing through the armature, it's impractical. Now the value, which is second value, is 19 amps. So it could be the possible answer for the armature current. Now if with these between these two, we have to choose the correct possible practical value for the armature current. Now we got the IA value. Now let's go back and see where we have to substitute. So this is the equation, V into IA plus IF, that will give us the input rated power, and then we can calculate the efficiency. So my efficiency at rated is equals to P output by P input. It's rated. My output is 2500, 2.5 kilowatt. My input is 150 multiplied by, this is IA plus IF. My IA is 19.413 plus IF is 0.75. Now into 100, because it's in percentage. Can someone tell me the answer, please? This will give us the percentage efficiency. 19.413 plus 0.75. So I'm getting a percentage of 82.659. So 82.659 percentage. So yeah, please tally these results with me, and you also please solve and tally the answer with me. So yeah, it's a bit lengthy problem. It's only lengthy because we have to calculate the armature current at the rated condition, where the data is given for the no load condition. So it's like we have to calculate the losses first, and substituting the losses we have to calculate the IA, and in substituting that IA in the efficiency equation we have to calculate the efficiency. So it's a bit lengthy, but it's very simple if you understand the concept of the DC machine, DC shunt motor construction, and DC shunt motor current division and power flow equations. It's very simple. It's nothing but substitution. See, we were given with the data, and then we wrote the equation of the efficiency. From that we found out that armature current value is missing, and to get the armature current we went with the power flow equation. With that we calculate, and then we found out that rotational losses is missing. So to calculate the rotational losses we went with the no load data. From that we easily got the rotational losses, and then we substituted, we calculate the IA, and then we calculate the efficiency. It's a bit simple but a bit lengthy. Now we will see the second numerical. It's very similar to the problem just solved, but if you read the question, there is an additional parameter which was given to us, which we haven't discussed till now. So let's read the question with me. An 8 kilowatt 240 volt DC shunt motor. 8 kilowatt means that's the output shaft power. The supply is 240 volts. Is drawing 2 ampere current from the supply at no load. Again we were provided with the no load current, 2 amps. Okay. Armature resistance is 0.5 ohms and field resistance is 480 ohms. And total brush drop. You see, 1 volt is a brush drop we are experiencing. I think the video has stuck. Okay. So the brush drop means whenever current flows through. Hello.
Ji sir.
Yeah. Am I audible?
Yes sir, you are audible.
Okay. 1 second. Yeah. So what exactly the brush drop means? It is saying that there is a 1 volt drop at the brush. It means whenever my current passes through my brushes, I am having a power loss at the brushes. So I am losing 1 volt drop at the brush side. So whatever amount of current flowing through my brushes, multiplied this voltage will give me the power loss at the brushes. Now, along with the power loss at the field, power loss in the armature, rotational power losses, I am having an additional power loss, that is nothing but the brush drop. So while calculating the no load losses in the machine, just like in the last problem, we just have to include the brush drop in this problem. Apart from that, everything is exactly the same. Now, I want everyone to solve this problem with me, and I will just go quickly in this problem because everything is same except that the brush drop is given. Now I will just discuss the brush drop equation, power flow equation with you, but apart from that, rest everything is same. Now, yeah, how we started. Now I will just draw the equation, like sorry, the diagram for the DC shunt motor, and this is supply, and this is 240 volt supply, and my field resistance is 480 ohms, and these are my brushes. I'm losing 1 volt here, of course, and this is armature resistance, and this is EB, RA and EB. RA is equals to 0.5 ohms. EB, no information about EB. Now, yeah, it is drawing some supply current. This is drawing taking some IF, and this is IA. Of course, I cannot calculate IA at the full load, but what is the value of IF? IF is easy. IF is equals to again 240 divided by 480. It is exactly half. So field current is 0.5 amps. Now, what is the data it was given? It's 8 kilowatt motor, 240 volts, and supply current at no load is equals to 2 amps, and V brush is equals to 1 volt. This is the extra information, additional data. So armature resistance is 0.5 ohms and field resistance is 480 ohms. Now, what exactly is asked? Again, efficiency at full load is asked. It is nothing but output full load by input full load. Do I know this? Yes, it is nothing but 8 kilowatt. Now I have to calculate the input full load. Again, what is the formula for input full load? The supply voltage 240 multiplied by IL. Now I know this V, but I don't know this IL, that is 240 multiplied by IA plus IF. IF is 0.5. Now the only quantity I required is again IA. Now how to calculate this IA? From let's first calculate the rotational losses, because from power flow diagram again I will take the same equation because I need an equation in IA. V into IA, power input to the armature, is equals to output power, net output power plus rotational losses plus armature copper losses. Now I know this output net power, that is 8 kilowatt. Do I know this armature? I don't know because it is IA square into RA. I need IA, and this again, this rotational losses. Now how to calculate this rotational losses? Again, the no load data. Here that brush drop will come. So here I want you to pay attention because brush drop is a new concept. So yeah, no load power loss is equals to, what are all the losses? Field copper loss at no load, armature copper loss at no load, rotational losses. I am not writing no load or full load because rotational losses is same for any load. Now P brush loss at no load. See, now How should I calculate this no load? My supply multiplied by IL no load, right? IF no load square multiplied by RF, this, and plus armature copper loss at no load is IA no load square multiplied by RA rotational losses, that is what I want to calculate, P brush drop voltage multiplied by current flowing through brushes at no load. Now this is one important point I want to say. Here are the location of the brushes, right? What is the current flowing through the brushes? It's nothing but the armature current. Now to calculate the power loss of the brushes in no load, I need to multiply that voltage with armature current at no load. That will only give me the power loss of the brushes, right? Now, yeah, it's just a simple substitution now. Voltage is how much? 240. 240 multiplied by total supply current at no load is 2 amps. 2 is equals to, what is the field current? It's 0.5. 0.5 square multiplied by RF. RF is 480. Now my IA will be, if it is 0.5, it is supply is 2 amps, my RA will be 2 minus 0.5, that is my armature current. Now square multiplied by RA, how much is RA? Armature resistance is 0.5 plus P rotational, that is what required, plus brush drop voltage is 1 volt multiplied by IA, that is armature current, is total supply current minus field current. Now from this only unknown is P rotational. Can someone tell me how much is P rotational? I will also calculate. It's 240 into 2 minus 0.5 square into 480 minus 1.5 square into 0.5 minus 1.5. So I am getting a P rotational loss of 357.375 watts. This is the rotational loss I am getting. Please everyone tally with me. Now since we got the this is the equation, main power flow equation.
Sir,
Yes.
I have get 343.5.
How much?
Please, 343.5.
343 you got.
Can you? Yes, please check it.
I got 357. 240 into 2 480 minus 0.5 square into 480 minus armature copper losses 1.5 square 1.5 square into 0.5.
Sir, you are right.
Okay. It
Right.
might be some calculation mistake. No problem. Okay. Yeah. That's why you also, if you also solve with me, we can mutually see where we have gone wrong. Okay. So P rotational is 357. Now let's substitute this P rotational in equation 1 from equation. Let's say it is 2 because last problem we have take it as 1. We took it as 1. Now substitute P rotational in it and we will get a quadratic equation in IA. Now V into IA, 240 IA is equals to output power, it is 8 kilowatt motor plus P rotational 357.375 plus armature copper loss, it is IA square into RA. How much is RA? 0.5. Yeah. Now it's a quadratic equation and please tell me the two possible answers for the IA. Please solve the quadratic equation. I will also solve with you. Okay, the two values I got are 442.2 amps and 37.79 amp. 37.79. Okay, now again, this 442 is a bit impractical. The armature current cannot be that high, and 37.79 seems to be a feasible full load armature current. Now again, select this 37.7, and now it's just substituting the value of IA here to get the full load efficiency. Now my efficiency full load is equals to power output full load by power input full load. My output power is 8 kilowatt motor. Input is 240 multiplied by armature current 37.79 plus field current. How much is my field current? 0.5 into 100 because it's a percentage. Now can someone tell me how much efficiency we got for our machine? I got 87.05%. I hope you also got the same efficiency.
Yes, sir. Yes, sir. Same.
Okay,
Yes,
great.
sir, same.
Okay, great. Thanks for confirming. So yeah, this is how we calculate the efficiency of a any DC machine. So what difference it will be if it is a DC series motor? If it's a DC series motor, again we just have to calculate the current flowing through the armature. But now the series current is same as the armature current, which is again same as the field current. Now that's how we calculate. Now even in the field copper loss also, the current will be there, and again we have to calculate the supply from the current. If we know the supply from the current, it's simple. So that's the same current flowing to the armature as well as field. So then we will get another kind of equation. It just depends on what kind of motor it is, whether it is separately excited, whether it is series or shunt. Based on that, our armature current division will change. So just look back at the question again, and let me know if you have any doubt in this question. It's exactly similar kind of question we solved before, but the additional thing is there is another added loss in this. Previously there is no power loss at the brushes end, but here we have a 1.5 watt. Is it 1.5? Yeah, we are losing 1.5 watts at the brush end. A little bit of power we are losing at the brushes. So that also we have to consider in the no load case. So yeah, let's just look back at today's discussion. We started with a little bit revision of the power flow diagram which we discussed few weeks back, and we saw what are all the losses present in a DC machine right from input to the output, and we saw that field copper loss will be there, armature copper loss will be there, and friction windage losses will be there as a rotational losses. And with that as a prerequisite, we started discussing DC shunt motor equations, and we started solving two numericals. And in each numerical, we were provided with the no load data as well as the ratings of our machine, what supply we are giving, and what is the output power of that motor. And we were asked to find the efficiency. So with efficiency equation, we came to know that we just need the armature current flowing through the armature, that value. So the important key point in this problem is that equation. So you have to get that idea of writing that equation. Now, if you don't know how to calculate the IA, quickly you have to remember that, okay, I know the power flow equation in which IA is there. I have to get some relation between IA so that I can solve for IA. So that is the key point in this problem. You have to remember that how you can relate the concepts you learn to the numericals. Looking at the power flow, it's simple. Okay, input is there, field copper loss is there, armature loss is there, and the output will be there. But applying that concept in solving a numerical is what the key solution is. So that's how you should get the idea. Okay, I have the power flow equation. From that, I can get a relation between armature current and other parameters. So if you able to get this equation one, and it's all simple then. So we got the rotational losses, and we substitute the calculate the efficiency. And yeah, so this is the another problem we solved with a brush drop included in this. The same procedure we followed, but while calculating the no load losses, we included the no load brush losses as well, and then we calculated the efficiency. So if you have any kind of doubt in today's discussion, please just ask me here. And if you have any doubts in rest of the concepts also, please point out. We will try to answer you. Or if I am not able to answer right now, I will get back to you in the discussion forum, or I will reach out to you personally, or we will update the answers in the discussion forum directly. So please don't hesitate to ask any kind of doubts, and I hope this will help you in solving the assignment problems as well. And a reminder for you all, at 7 p.m. today there will be another session taken by one of my fellow colleague. So please do attend that session as well. He will also be discussing some concepts on DC shunt motor and how to calculate the efficiency, how to calculate the voltage regulation, and some concepts. Yes, Saurabh.
Sir, night sessions to related to week 12.
Sorry, next session.
Night sessions will be 12 week solution.
Yeah, 12th week.
Okay, sir.
Yeah. So yeah, please join that as well. We will be discussing 12th week in the 7 p.m. session as well. Yeah. And since it is a 12-week course, this will be officially our last session, and this will end our discussions on DC machine, electrical machines course 1. Now, this will be last session entirely. Of course, there will be one more revision session or revise session next week. We will be mailing you, or we will be letting you know when that session will be taking place, or how that session will be in the next due course of the week. But there will be one more session as a revision, but apart from that, all our concepts have been covered. I hope all of them are covered with this 12 weeks of discussions, and whatever doubts you are having, or whatever concepts you are having doubt, you will see in that revision session. That will help. Yes, sir.
Sir, ideas there about the NPTEL exams, machine 1.
What are you asking?
Sir, share some ideas to related NPTEL exam.
Okay, exam.
Machine 1.
Okay, machine exam. When was the date given to you for the NPTEL exam for this course?
29 October. 29th October.
Okay, 29th of October. See, these questions will be entirely numerical, as well as there could be conceptual questions. But if you just go through all the assignment solutions and you just practice all our 12 weeks of assignment problems, and it will be very easy for you to solve. So you just learn the basics well, and what are all the concepts we have discussed in the transformers, and of course revising each and every lecture now will be difficult. So You revise this discussion sessions at the end of the day, end of the week we did, and you again practice all the assignment problems as well, and also just read some basic concepts in transformers and DC machines. Before, like in every session, we discuss numericals, but before going into numericals, we discuss some concepts. Yeah. So I hope you got the idea. You just solve all the assignment problems again, and this all the quiz questions. I mean, and you should be thorough of all the basic concepts in DC machines and transformers. So if you are able to understand our discussions and you're able to solve the quiz questions, it will be easy. There is no need to worry about it. The exam, it will be easy only.
Sir, all questions are numericals based.
No, I can say that because I don't know how the pattern of the questions will be, but definitely numericals will be there. And if at all they want to ask any conceptual questions, even they can ask because even we don't have that information right now. So yeah,
Okay, thank you, sir. Thank you.
yeah, sure. So yeah, with that, one second. Okay, so with that, let's end our session today. And I thank you everyone for attending the session and listening to me patiently and solving the questions along with me and having a good discussion with me. So yeah, thank you for giving me this opportunity to take NPTEL sessions with you all. It's been really a good 12 weeks of discussions with you, and I have learned a lot during these 12 weeks. Yeah, I hope you also have some kind of advantage by from these sessions. I hope you are also gained some subject and concepts from these 12 weeks of discussion. And I hope to meet you all again.
Thank you.
Thank you.
Thank you, sir.
Thank you.